And our final speaker of the session is Andrew Strominger from Harvard, who's going to tell us about the nature of time in string theory.
What comes off in this? Can you pour me a glass of water there? Can you pour me a glass of water? Okay, I'd like to start by thanking the organizers for a wonderful conference and also for arranging such beautiful weather. So I'm going to talk about the nature of time in string theory. So over the last 15 years, is there a laser pointer or? Over the last 15 years, we've had a continual parade of amazing results coming out of string theory, but all of them have had a rather similar character. They all involve static configurations. So we, in particular, time is something that's remained fixed. Time and quantum mechanics have not been toyed with at all. On the other hand, we've learned a lot about the nature of space. And one of the things that we've learned about space is it's almost certainly not a fundamental concept in string theory. There are different dual representations of the same, which describe the same object as different spatial objects, and T-duality, R going to 1 over R. We don't even know whether something is big or small. So space is clearly not a fundamental concept. Now I'm going to put my hat on the chopping block here. And, you know, in general relativity, space and time are on the same footing. And if space is not a fundamental concept, I don't see how time can be a fundamental concept. But of course, for quantum mechanics, we really need an exact notion of time. And so in our efforts to understand what happens to time in string theory, I think we should be prepared to challenge the sacred cow of quantum mechanics. Now, I noticed this morning Tom Banks, in his talk, challenged almost every sacred cow except for time and quantum mechanics. So I'm trying to complete the circle here. So I think an obvious next step, this is certainly a sentiment shared by a large percentage of the speakers, is to study, just to try to start to study the nature of time in string theory and see where it leads us. Despite the title of my talk, I'm not going to answer it for you. But why do we want to study the nature of time? What are the interesting questions that we could try to learn? Well, for a theory of everything, string theory has had remarkably little to say about the origin of the universe. And that, of course, is a time-dependent phenomena. Another time-dependent phenomena is what happens to an observer that falls into a black hole. Can we resolve the singularity, Schwarzschild singularity of a black hole by some analog of the many beautiful tricks that we've used to resolve time-like singularities in string theory? Another puzzle is that if we regard string theory as a cutoff at the string scale or at the Planck scale, then we would expect space to have some number of degrees of freedom per unit Planck volume. But if the universe is expanding, then there have to be more and more degrees of freedom as time goes on. Where do those degrees of freedom come from, if they really do appear? Another problem is understanding the entropy of horizons associated with observers as in de Sitter space. Now, I think you'll all agree that our current bag of tricks don't tell us how to answer any of these questions, but we can look for new tricks by studying time-dependent configurations. Sorry, what time did I start? 5:22. 522, okay. Now, there's no obvious path. I don't, or at least I don't have an obvious path to the answer to these questions. But there are still things we can do that I believe will move us forward. We can think about what general kind of phenomena we might expect. We can try to take all the, and this is much of what I'll be talking about today, we can try to take all the static phenomena that we've studied in string theory and just sort of turn them sideways and see if there's some time analog of them. And of course, as to quote David Gross, when in doubt, calculate. We should look for models that have something to do with time and try to calculate something and see where we get. And we always learn something when we do that. And we've seen a lot of that during this meeting. Now, the rest of the talk is going to describe my own explorations in time-dependent phenomena over the last year. I'll really just be giving some highlights since I'm now down to 18 minutes. But a lot of other people have worked on this, and as soon as I started to write this, I realized how silly it was because I think the names just keep going on and on of people who've tried to understand things about time and string theory. But I should mention my own collaborators, Busso, Gutperl, Maloney, and Silverstein. Okay, so I'll start by describing one of the most simple, but yet still extremely enigmatic time-dependent geometries, and that's de Sitter space. So here's a picture of a Penrose diagram in de Sitter space. It has a past infinity, a past space-like infinity, and a future space-like infinity. And the fact that this diagram is a square represents the fact that a light ray starting at the North Pole at t equals minus infinity will just reach the South Pole at t equals plus infinity. Now, in in spaces which are just asymptotically de Sitter in the future, an important example of which may well include our own universe, it's often the case that one doesn't have a past de Sitter region, but that half of the de Sitter space is cut off somewhere near the past horizon and replaced by a big bang or inflationary era. So with that in mind, though one can consider the whole de Sitter space, with that in mind, I'm going to mainly be considering this upper triangular region of de Sitter space, which is the future, causal future of an observer along the South Pole. Now, this region here is called the causal diamond. It's the region of de Sitter space where experiments can be done. If you want to know if you're on the South Pole and you want to know what the weather is anywhere in de Sitter space, it has to be in the causal diamond. You can ask what the weather is in this region, but they'll never be able to tell you. You can't ask down here, though that they could tell you anyway. But this is the region where we can really do experiments. Now, what do we want to learn about de Sitter space? Well, my favorite question about de Sitter space is, as you all know, de Sitter space has a temperature and an entropy given by 1/4 the area of the event horizon. Now, every other kind of entropy that occurs in nature, including most kinds of black holes, we can now understand in terms of counting some sort of quantum microstates. And we should try to do the same thing for de Sitter space. But it's very puzzling how we're going to manage to do that, because unlike the case of a black hole, this horizon moves around with the observer. If we had an observer with a world line like this, then he or she would have a different horizon. So it's hard to know how to even get started on that question. Nevertheless, I think it's a very nice question because it's very sharp. If you have some calculation and you do it and it gives you the right number with the 1/4, then you'll know that you've learned something. Now, other questions are, what are the observables in de Sitter space? Is there something like an S matrix? Does it make sense to talk about something like an S matrix where particles come in from the past and go out in the future? Now, I'd like to point out right in the beginning here that one encounters a very basic and fundamental tension in trying to answer question 2. In other words, in trying to understand what are the physical quantities we'd like to compute in de Sitter space. So the first, and this tension comes from the following 3 points. The first is that in quantum gravity, there are no local diffeomorphism invariant observables, because points get moved around by diffeomorphisms. And one of the great lessons that we were already partly aware of, but was really hammered into us in the context of ADS, is that ADS-CFT, is that the observables you really want to discuss are best associated to an asymptotic boundary where you keep the metric fixed and don't integrate over it. So in ADS, we think of the observables as living on the boundary, and we believe that that's a complete set of observables. All right, so that's one thing we believe to be true. Another thing we believe to be true is that if we don't, we should only discuss physically observable quantities. We often, in the history of physics, we get in trouble if we try to discuss things that are not physically observable. For example, those who try to construct quantum theories involving both position and momentum were doomed to failure. So we might think that our troubles with understanding de Sitter space will be alleviated if we stick to observable quantities. Now, those observable quantities are confined for any given observer. They're confined to one of these causal diamonds. Which causal diamond, of course, depends on what the observer is. So the third point is that this causal diamond, the interior of this causal diamond, has no intersection with the boundary. So we're caught trying to choose between things we know and love, that you should stick to the boundary if you want good observables, and that you should stick to things that you can see if you want good observables. And I don't know how we're going to reconcile this, but I'm going to ignore 2 and 3 for now, and I'm going to try to follow the program in ADS towards understanding what we should be calculating in DS, but remembering I may be punished for forgetting about the necessity of restricting to observables. Okay, so now here's an example of what I want to do here is to try to take some of the things we've learned about static behavior in string theory and just turn them sideways into the time-dependent context. And in particular, I want to turn ADS-CFT holography sideways to get some kind of DS-CFT holography. And here's how I want to set it up. If you look at these null coordinates for de Sitter space, slices of constant v start at the south pole and they go up and they end on scribe plus. And in fact, you can deform these slices so that they're space-like and they end on scribe plus. Now, it's a surprising and bizarre feature of de Sitter space that you can have space-like slices that end at future infinity. You certainly can't do that in Minkowski space or anti-de Sitter space. But it's going to be very useful to us here. So what I want to do is set up the Hilbert space on these slices. Now I want to talk about time evolution. And there's a killing vector in de Sitter space, which I call L naught, which is everywhere future directed within the causal diamond. And furthermore, this killing vector marches us along these slices in the direction of increasing V. So the way I'd like to describe the Hilbert space is on functionals on these null or space-like slices, which end at the boundary of the space, which in this case happens to be Scri+. So if we set up the Hilbert space that way, if we think of de Sitter space that way, then the analogy to ADS, the obvious analogy to ADS-CFT becomes clear. This killing vector is generating time translation along the slices, but if we look at what it does up on Scri+, it's just a dilation. It's moving in a space-like direction, dilating everything on Scri+. So the structure of the killing vector here tells us how we should be adapting there it goes. Okay. How we should be adapting ADS-CFT to DS-CFT. And so the DS-CFT conjecture is that bulk physics in this region is holographically dual to a field theory that lives, a conformal field theory that lives on the boundary, and time translation in the bulk is dual to scale translation in the boundary. So that's like the statement in ADS that that scale transformation on the boundary is dual to radial transformation in the bulk. We just turned it sideways. But this brings us to something really quite radical, and that's the idea that time itself is the direction that is reconstructed by holography. Now, there's been a lot of work on this over the last year, and there's some evidence for it. First of all, the isometry groups match. You can do a Brown-Hanot type analysis in 3 dimensions and show that correlators on the boundary must obey the Ward identities of a conformal field theory and even compute the central charge. It seems to work in Hull's 2 star theory. And a lot of gravity calculations flesh out a self-consistent picture. And I would summarize it by saying overall the evidence intrigues us to think about it further, but it's not compelling. And it's not compelling because we don't have any of the concrete examples like we do for ADS-CFT in string theory, and we need to try to embed this structure into string theory, and I'll come back to that in a little bit. But let me just talk a little bit before that about cosmological applications. So our own universe is not de Sitter now, but it may well be asymptotically de Sitter in the far future. But since it's not exactly de Sitter, it couldn't be dual to a conformal field theory on the future boundary because the isometry groups wouldn't match. So just as in ADS, where radial transformations are identified with RG flows in non-conformally invariant boundary theories, here I would like to identify time translations as RG flows in a general field theory that would live on the boundary of Scri+. Now, what is the Big Bang? So how does this fit into our own universe? So in our own universe, we have an asymptotically de Sitter region. We have a present era. We have another conformally invariant region of inflation. And then we have possibly a Big Bang. And in a scenario like this, what would a Big Bang be? Well, Big Bang would be, after you get to the Big Bang, there's going backwards in time, there's nothing else. So it's like a trivial infrared fixed point. And this kind of thing has been studied in the radial context, where originally supergravity solutions showed a singularity at some finite radius, but then it was understood that the field theory confined at that point and developed a mass gap, and there was no physics beyond that. So in this kind of proposal, the Big Bang is a trivial infrared fixed point. And this is another example of trying to take mechanisms for resolving time-like singularities in string theory and turning them sideways. Now, we had a beautiful classification by Horowitz the other day of proposals for the origin of the universe. And I think that this falls in the C, other category. Would you agree, Gary? What? I don't think it is Hartle-Hawking. Think it's Hartle-Hawking? Now, what this completely reworking the universe in this way completely changes what is and isn't natural. For example, and I'd like to compare this with comments that Tom Banks made, in this theory, the value of the cosmological constant in the future is an input data of the theory. It's related to the central charge of the ultraviolet fixed point, and no renormalizations of the boundary field theory will change that. So there's no fine-tuning issue of the cosmological constant, though one still has to understand the origin of the large ratio. Now, it's not exactly what Tom was saying, because this theory, though maybe we look at it a different way, it will become exactly the same thing. But because this theory actually, it's an infinite R3, so there are an infinite number of degrees of freedom up there, but still it's closely related. And also, there's a dictionary that has been developed by these people between the parameters of inflation and various anomalous dimensions and beta functions of the infrared fixed point, and it changes the idea of what's natural. Okay, now I'm going to put my head on the chopping block again. And one of the peculiar features of this is that in this picture, the degrees of freedom of our universe are continuously integrated in with the inverse RG flow. That is, at the Big Bang as an infrared fixed point, there's no degrees of freedom, and as you move forward in time, they gradually come into being. And this is why I think it's different than Hartle-Hawking, which I think is unitary once it's produced, though maybe there's some other way of looking at it. But outside of this DSC-FT proposal, I really think we have to think about this, that if we say that time has a beginning, we're in trouble with unitarity. Because, you've got some quantum state, it evolves with a phase. You've got it now, unitary quantum state, evolved back to the beginning of time. What keeps you from just keeping evolving back past t equals 0? So I think that there's some fundamental tension, but Tom has some idea how to do it. He's shaking his head. But I think there's some fundamental tension between unitarity and a Big Bang. Now, how would we get out of this? Well, maybe there's some dual picture in which things are unitary. Maybe we'll be so stuck on unitarity that we'll have an ekpyrotic universe, or maybe we'll have some mechanism like what Liu, Moore, and Seiberg had, where you have some big crunch and you can attach it onto a Big Bang. Did I really start at 5:22? Okay. All right. So we'd like to embed this in string theory, and there are two things we could try to do. One would be to find de Sitter solutions of string theory, and the other would be to try to find Euclidean field theories, which are candidate duals of time-dependent string solutions. And Gutperl and I have been studying these, the so-called space-like branes, or S-branes. And it's a very simple idea. In 2A string, unstable D3 brane of 2A string theory, you have a tachyon with a kink solution, which gives you an ordinary D2 brane. But there's also an S2 brane solution of the same theory, where the kink is in space, in time rather than space. And it carries some kind of Ramon quote-unquote charge, which is measured not by a spatial sphere surrounding the D2, but by a sphere which has some space and time components which surround the S2. Now recently, I guess I'm just going to go through this fast. Recently, Sen has found these exact conformal field theories which represent these S-branes. And one can also, they're presumably exactly soluble, though no one's done so yet. And one can also talk about a half an S-brane solution, which is related to a boundary Liouville theory. And trying to understand what happens on these S-branes to the open string spectrum is another interesting exercise and some concrete calculations in open string theory. And what I've done is to compute the particle production of open string modes on a decaying S-brane. And, okay, I see Michael coming over. So, well, what happens is that as the S-brane decays, you get a lot of particle production. And in fact, it sort of tries to produce at a temperature higher than the Hagedorn temperature. And I believe that the brane dumps all of its energy into, first of all, into open string particle production, which then couples to closed strings. So I believe that the brane dumps all of its energy into closed string in a time of order G string to 0. And it struck me as I was listening to Eva's talk that that might be her non-local world sheets might be, this might be a very interesting, bilocal world sheets, this might be a very interesting place to apply those ideas to get the outgoing open string state. So what's the best of all possible worlds in this discussion? Well, the best of all possible worlds is that we can understand some time-dependent open string theories, take their large N limits, and say that they're holographically dual to some time-dependent closed string cosmology. And the worst of all possible worlds is that we just continue to thrash around and learn some more things about time-dependent open string theory. And am I red? I'm very red. Okay. Well, and so my conclusion then is that understanding the nature of time in string theory is a challenging and exciting problem. There are lots of concrete things to work on, but there's also a big reward out there that we may be able to understand some of these really interesting conceptual questions.
So, questions? Gary.
So, in Ashok Sen's talk, he described, say, the annihilation of a brane and an antibrane in terms of this tachyon and the energy state in the tachyon node. Now, in your calculation of the particle, the open string creation, are you extending his calculation by adding a little bit of string coupling to produce the open string?
I'm extending his calculation, yes. So there's no open string pair production at G string strictly equal to 0. It's a quantum effect. However, if you make G string very small, you find that the open string pair production, actually the energy produced into open string because of a Hagedorn-like divergence goes to infinity at some time of order the string time. So it becomes, the whole system becomes strongly coupled at the time of order the string time. So the question is, what so it's not clear that the G string goes to zero limit is smooth because of this divergent open string production. Clearly, eventually, everything goes into closed strings, and the question is whether it happens in a time of order 1 in string units, or the most it could be is a time of order log G string.
I just wanted to comment about this issue of unitarity. In general, if you have a time-dependent Hamiltonian, the time evolution operator doesn't form a unitary group of operators. Greg Moore taught me that it's called a groupoid. You just have a unitary operator for pairs of points. And there's nothing that prevents you from stopping the evolution at any time that you want. You just set the Hamiltonian equal to 0 before some time. And so I don't think there's really an issue of a Big Bang in unitarity once you get away from the notion of time-independent Hamiltonians.
Can we stop right now? When are we allowed to stop?
Not before dinner.
All right. That looks like all our questions. I want to thank Andy and all the speakers this afternoon.